Alright, so welcome to the 5th lecture. Today we're going to talk about the cross-flow heat exchanger. So we have 2 more lectures for this semester. We have this one, and then the next one is also going to be on a heat exchanger, but in that case it'll be a double pipe heat exchanger. Okay, so now we're kind of getting into the heat transfer part of the course where we have these last 2 experiments. Okay, so like I said, this one is going to be on the cross-flow heat exchanger. Okay, so this is kind of what the heat exchanger looks like. We'll talk about that a bit later on. So our objectives for this experiment, we want to measure the heat transfer in the cross-flow heat exchanger composed of a single copper pipe. Okay, and then we're going to measure the heat transfer in the same heat exchanger, but now we're going to have a single copper pipe, and then we're going to have a full row of dummy rods. And then we're going to do this again, but now we're also going to have a full bank of dummy rods. And then we will investigate the relationship between the Nusselt number and the Reynolds number. So we'll talk about that a bit more in the lecture as well. Okay, so these dummy rods, basically they are just clear plastic rods that we're going to insert in the heat exchanger. So let's go back up here. Basically this is just a simple model of the cross-flow heat exchanger. So we're going to have some fluid flow going through these tubes here, and then we're going to have this cross flow, it's called here, that's going to be perpendicular to the flow through the tubes. So this cross flow is going to be air that we're going to be kind of sucking into the system. Basically what this is going to do is it's going to convectively cool these rods here. So we're going to be using, one copper pipe that's going to be heated up, and we're going to cool that with convective cooling. So let's go down. Let's go here. So this is what the setup kind of looks like. I don't have an actual picture of the setup, so just gotta use this schematic here, but basically what we're gonna have is we're gonna take in flow, we're gonna suck in air basically into our system here, and that's going to go into this test section right here where we have all of our rods. Okay, and then we're gonna have that convective cooling, and then we're basically going to collect some data where we have a data acquisition system that's going to basically record everything for us. And what we're going to do is we're going to plot our dimensionless temperature distribution here versus time for all 4 throttle openings. So that's kind of like what we did in lab 2, where we adjusted this opening here to increase the flow rate. Okay. And then we're going to find the heat transfer coefficient for each run. And we're going to be finding that from an equation that we're going to develop in a lecture, where the heat transfer coefficient will basically be the slope that we have from this equation. Okay, and then we're going to see if we can actually apply our lumped system assumption that we're going to use. So we're going to make this assumption basically to make our calculations a bit easier. And if you remember from your heat transfer class, this is only valid if our Biot number is less than 0.1. And then the last thing for part 1, we're going to calculate the Reynolds number and the Nusselt number for each run. And then basically what we have here is different kind of configurations, and we're going to be repeating all of this stuff up here. Okay, and then on number 4, we're going to plot the Nusselt number versus the Reynolds number for all of these different configurations that we have. Okay, and then for the last thing we're going to do, we're going to calculate the downstream velocity profile. Okay, so for that we're using a pitot tube once again. So if I go up here, so we have a pitot tube, so we're going to adjust that radial position kind of like we did in lab 2 as well. Okay, so that's basically what we're going to do in the lab. The air analysis here, this is basically a differential air analysis that I don't require. So with that, we're going to go ahead and get started with the lecture. Okay, so the first thing that we're going to do is define what a heat exchanger actually is and how the heat is going to be transferred in the case of a cross-flow heat exchanger. Okay, so what we have here is a heat exchanger is a device that transfers heat between two fluids at different temperatures that are separated by a solid wall. And this heat transfer is going to occur due to these differences in temperatures. So for this experiment, like I said, we're going to be using a cross-flow heat exchanger. So for a cross-flow heat exchanger, you can either have the schematic for the figure A, or you can have the schematic on figure B. For us, we're going to have the schematic for figure B. We're not going to have a finned surface. In this case, what we have here is the unfinned surface where one fluid is kind of called mixed and the other fluid is going to be determined or called unmixed. So in this case, the unmixed fluid is the fluid that is going through the tube wall. Okay, so in purple there, all of that fluid going through each tube that is unmixed because it's in its own tube. The mixed fluid is going to be the airflow that we have, and that's going to be this cross flow. Okay, so in blue there, that's our airflow. It's mixed because this airflow, it's allowed to mix as it goes over the tubes that we have. So what you would see if you were kind of looking at this profile from a kind of side view here, our airflow, it would be, going over this tube, and maybe some would go under the tube at the end, some would go over the tube at the end. So what you have is all of these kind of streamlines of the airflow that we're going to have, and they're going to get mixed together. There's going to be a lot of turbulence due to the nature of our configuration for this heat exchanger. Okay, and then for the lab, we have this airflow. Once again, that's our cross flow, but instead of having fluid going through our tubes, we're just going to have just rods. So remember, we're going to have some dummy rods that are just plastic rods, and then we're going to have one copper rod. So this is still a heat exchanger, it's still a cross-flow heat exchanger, but what we have is this airflow, or this cross-flow, it's going to cool down that copper rod that we have. The copper rod's going to be heated up to a certain temperature, and then it's going to be cooled down from this cross-flow. Okay, so what I have now is the heat transfer processes that you could have in a cross-flow heat exchanger. So the first one we have is convection from the inner fluid to the inner wall of the tube. So if we had tube flow, if we actually had flow going through these tubes, so again I'm drawing that in purple, we're going to have convection from that fluid that's flowing in the tube to the tube wall. At this point, we're going to have conduction. That's going to be conduction through the wall, so this is our kind of resistance that we have. Okay, so if we have a thicker tube wall, then we're going to have more resistance there. So if we want to increase our heat transfer, we should have a thin wall with a material that is highly conductive. Okay, and then the next heat transfer process that we're going to have is convection once again. This time we're going to have convection from the outer surface of the tube to the outside fluid. Okay, so that's when we have our cross flow here. From this cross flow in blue, that's going to be going over the tube, so we have convection between that outer fluid and the outer surface of the tube wall. Okay, so for this experiment, the convection that we're going to have, that is going to be the primary source of heat transfer. And then, as we already kind of noted, to maximize our heat transfer, the wall of our tube should be as thin as possible, so we can reduce the thermal resistance. And then we want to have our material to be highly conductive, so in this case we're going to be using copper. Okay, so for this lab, we're going to be using a thermocouple to measure the temperature of the copper rod that we're going to use, and we're also going to use this to measure the temperature of the airstream that we have. So basically how this works is we have two different conductors that are going to form electrical junctions, and these are going to be at different temperatures. So what we have here is we have a hot junction and a cold junction. So the hot junction, that's going to be, in this case, the copper rod that we have, or it could be the airstream that we have. And then we have a cold junction, which is going to basically be immersed in an ice bath. Okay, and then this basically is going to create a voltage, and this voltage can then be kind of converted to a temperature. So we're going to be using this equation here for the thermocouple. So T sense, that's going to be the temperature that we're trying to measure. So either the temperature of the copper rod or the temperature of the airstream. Again, that's going to be set equal to the reference temperature that we have. Again, that's going to be an ice bath. And then we're going to add the voltage that is created, and then that's going to be divided by the conductivity of two different materials that we have. They're going to be two different metals. So we have a metal B and a metal A. They have to be different metals, because if they're not, then the conductivity, that's going to be the same, and our denominator is going to be 0. Okay, so now we're going to talk about the Nusselt number, or NU. So for this, it's for convective heat transfer, and it's a way to quantify the heat transfer that we have. So the second fluids, we had the Reynolds number, and that kind of quantified our flow. That was a ratio of inertial forces to viscous forces. For heat transfer, we have the Nusselt number, and that's going to be a ratio of the convective to the conductive heat transfer that we have. Okay, so we have nu equals HL over K, where H, that's going to be the convective heat transfer coefficient. This is going to be what we're going to be solving for later on. And then L is going to be the characteristic length of our kind of object that we're looking at. And then K is going to be the thermal conductivity of the fluid that we have. Okay, so in this case, for this lab, we have pipes. So L is going to be just the diameter. Okay. And then what we have here is we have ranges for the Nusselt number, just as we have ranges for the Reynolds number in fluid mechanics. So what we have for the Nusselt number, if it's approximately equal to 1, that's going to be a laminar flow, and if the Nusselt number is equal to 100 to 1000, that's going to be turbulent flow. That was not supposed to happen. Alright, so we have these ranges, and yeah, we're going to use those to quantify if it's laminar or if it's turbulent. Okay, the next thing we're going to talk about is the Reynolds number. So we're still going to be solving for that in this experiment because we have some airflow and we're going to be increasing that airflow. So knowing what the Reynolds number is going to be something of value to us for this experiment. Okay, so for a cross-flow tube bank, the Reynolds number, it's going to look very similar to what we usually have, which is rho v d over mu if we have pipe flow. But in this case, what we have is rho v max d divided by mu. So v max, that's just going to be our maximum fluid velocity. So what we're going to do here is we're going to simplify our Reynolds number here. We're essentially going to solve for v max, and you'll see that once we solve for this, this is going to be the outlet velocity that we have basically. So we're going to go ahead and kind of solve for this right now so we can easily calculate the Reynolds number for these or for this experiment. Okay, so what I've written out here are some assumptions or kind of physical parameters that we're going to have in the lab. So again, what we're going to do is we're going to solve for the maximum velocity here, and then we're going to plug that in to modify the Reynolds number that we have. So the first thing is we have a constant cross-sectional area duct. Then we're going to have two rods spanning the wall of the duct, and they're going to be lateral to the main flow direction. So we're going to start off this kind of procedure here with two rods, and we're going to alter this to be N rods so it could be a little more general. Then we're going to have a control volume defined by the walls of the duct. Then we're going to say that our inlet 1 is upstream of the rods and the outlet 2 is downstream of the rods. So if I go over here, didn't think it would go all the way back up, but that's okay. So here we have our test setup. Okay, so what I have here is I've kind of drawn the inlet here. That's inlet 1. It may not be right there, it might be here. I don't know because we're not actually in the lab. And then, but it's somewhere upstream of the rods that we have. And then our outlet 2 is going to be downstream of the rods. And then what we basically have is a control volume here, where again that's kind of bounded by the walls of our duct. And you can imagine that these rods that we have, they're going from one side of the wall to the other side of the wall. So that's going into the page here. Okay, so that's our kind of test setup here. And what we're going to do now is we're going to apply conservation of mass, and then we're going to solve for this outlet velocity V2, which will then be the maximum velocity that we have. And we're going to go ahead and plug it into the Reynolds number. Okay, so we have rho 1 V1 A1 equals rho 2 V2 A2, where the velocities are going to be an average velocity that we have. Okay, so now we're going to go ahead and solve for V2. Okay, so V2 is going to be equal to V1 multiplied by the ratio A1 divided by A2, and we took out rho because we're going to assume that the flow is incompressible. Now for our geometry here, I'm going to define what the areas are. Okay, so we have A1 equals the width times the height, and then A2 is going to be the width times the height minus 2 times the width times the diameter of the duct. Okay, so now what we're going to do is we're going to plug these in, and we're going to solve for V2 once again. Okay, so now our outlet velocity is going to be V1 over 1 minus 2 times the diameter divided by the height of the duct. Now remember, we did this based on the assumption of having 2 rods in the system, so we're going to go ahead and just change this to n rods for the system, because we have more than 2 rods. And then we can go ahead and plug that in, so we have a generic form for the outlet velocity for this cross-flow heat exchanger. Okay, so all I did is replace the 2 with an n, and now we have our expression for the maximum velocity in this heat exchanger system that we have. Okay, so now we can go ahead and plug this into the Reynolds number, and we can have the final form for the Reynolds number that we're going to use for this experiment. Okay, so we have our final expression for the Reynolds number. We have just rho A, where rho A, that's the density of the air, multiplied by the inlet velocity times the diameter, that's a d, all over the viscosity of the air multiplied by 1 minus n rods multiplied by the diameter over the height of the duct. Okay, so we're going to go ahead and use that formula for our data reduction when we have to find the Reynolds number. Okay, so now we're going to talk about the transient heat transfer in a lumped system. So we'll begin by talking about what a lumped system is and how we can verify if we have a lumped system. And then we're also going to develop some equations so we can look at some things like the non-dimensional temperature difference and the time constant for the system. And also we're going to use all this to develop a linear equation so we can solve for the convective heat transfer coefficient. Okay, so basically what we have is a lumped system is going to reduce a thermal system into a number of discrete lumps, and all of these lumps that we have, they're going to be held at a constant temperature. So this is going to be useful for us because it's going to allow us to have an algebraic equation to solve for instead of a differential equation that we have to solve for. Okay, so what I've written out here is that our convective heating and cooling within the body and from the body to the fluid are going to be the same magnitude. So basically what this is saying is that our convection is going to be equal to our conduction. Okay, so if we write out those equations and we set them equal to each other, we can use this to develop a non-dimensional temperature difference that we're going to develop later on. So we have TW, that's the surface temperature of the boundary that's in contact with the fluid. Then we have the atmospheric temperature, we have the thermal conductivity of the solid, we have the characteristic length, which again remember is going to be the diameter. And then we have T1, that's going to be the internal temperature of our solid at a distance L from the boundary. Okay, so I realized that I accidentally wrote this equation a little wrong. Instead of being T1 minus T atmospheric on the right hand side, it should be T1 minus T sub W, or T wall. Okay, so then if I take the temperature ratio, I can have T1 minus T wall over T wall minus T atmospheric, and that's going to be equal to HL over K sub S. Now, some of you might kind of notice this term on the right hand side. That's going to be our Biot's number. So we're going to use this Biot number to basically later determine if we can use the lumped assumption or not. And again, this is going to be good for us because if we can use this assumption, we don't need to solve a differential equation, and we can just solve an algebraic equation. So what this is it's the ratio of the heat transfer resistances inside of and at the surface of the body. Okay, and basically this is going to again determine if we can use our assumption or not. Basically it's going to say if the temperature inside of the body is going to vary significantly while the body is being heated or cooled over time from some outside thermal gradient that is applied at the surface. So for our experiment, this is going to be of use because we are going to have a hot copper rod that we're going to cool over time from a cold airstream. So if we can apply this lumped assumption, it's going to make our equations much easier to solve. Okay. And then so what I've written out here is if the B out number is small, then the temperature ratio from equation star, which is at the top of the screen, that's also going to be small since they're equal to each other. In this case, small is going to mean much less than 1. So I can rewrite equation star to be T1 minus T sub W over T sub W minus T atmospheric. And I can set that equal to much less than 1. And then from algebra, I can just do T sub 1 minus T sub W is much less than T sub W minus T atmospheric. Okay, so now what we have here is on the left-hand side, you can think of this as the temperature distribution inside of our object. We have T1, that's the internal temperature of our solid at a distance L from the boundary, so right there. And then we have TW, again that's going to be the temperature at the boundary that's in contact with our fluid, so basically the wall of our tube. So what we're saying here in this equation is if that temperature distribution or difference is much less than T sub W minus T atmospheric, or that temperature difference outside of our object, then we can use this lumped assumption. Okay, so now what we're going to do is we're going to start to develop an equation for how our temperature is going to evolve over time. So what we're going to do is look at the rate of heat transfer that is coming out of the body, and we're going to look at the rate of heat transfer across the surface and to the fluid. So we're going to be setting those equal to each other after we develop them, and then we can start to develop an expression for our temperature over time. Okay, so what we have is the rate of heat transfer out of the body. That's going to be equal to rho, or minus rho, times the volume, times the specific heat over this differential kind of temperature distribution over time. And then we have the rate of heat transfer across the surface to the fluid, and that's going to be our cross-sectional area times the convective heat transfer coefficient multiplied by the temperature minus the atmospheric temperature. So just as we did earlier on when we set the conduction equal to the convection, we're going to do that once again, and then we can develop an expression for how the temperature is going to evolve over time. Okay, so what I've done now is I've set them equal to each other, and then I've non-dimensionalized them. So there's a little bit of hand waving here, but basically what we have here is at a time of t equals 0, then this is going to be equal, or the non-dimensional temperature is going to be equal to 1. Okay, so basically what we have here is that this is going to be in the form of a differential equation, a simple one that we can solve for. Okay, so we have the form dx over dt plus x over tau equals 0. So tau, that's just our time constant. That's m times c over h times a, where m is the mass, c is the specific heat, h is the convective heat transfer coefficient, and a is the cross-sectional area. And then we know from, a class like 308, that the solution would then be of the form x equals a times e to the minus t divided by tau. So we have an exponential here. And a, that's just going to be a constant to satisfy our initial condition, and we can basically say that a just equals 1. So our solution is going to be e to the minus t over tau. Okay, so then if we solve for this non-dimensional temperature difference using the kind of same logic that we had above, then we can rewrite this now as T minus T atmospheric over Ti minus T atmospheric is going to be equal to E to the minus HAT over MC. Okay, and then taking the natural log of both sides, we can rewrite the above equation. And basically, you'll be using this form for the left-hand side of the equation for part of the data reduction for this lab. Okay, so what we're going to do now is we're going to start to develop an equation so we can solve for the convective heat transfer coefficient. So the first thing we're going to do is we're going to look at the surface area of the copper rod that we have, and we're going to modify that equation to the physics that we actually have in this problem. Okay, so for our experiment, the heat on the rod is only going to be transferred from the lateral surface area on the rod. So a surface area for a cylinder basically is going to be pi times d times L, where d is the diameter of the rod and L is the actual length of the rod. However, we're going to have to modify this equation because there's really going to be a small amount of heat transfer on the end of the rods to the air. So to account for that, we're basically going to modify the length that we have in this equation to take care of that. Okay, so our corrected surface area is going to be a sub s comma CRT, where CRT just means corrected. So that's going to be equal to pi times d times L corrected, where our corrected length is going to be the actual length of the rod plus 8.4 times 10 to the minus 3 meters. Okay, so now we're going to develop the equation to solve for the convective heat transfer coefficient. So the first thing we're going to do is we're going to make some substitutions to this equation right here. So what I'm going to do is I'm going to let y equal to the left side, and I'm going to let b equal to part of the right side. You'll see what I mean. Okay, so now what I've done is I've made those substitutions where y equals just the left-hand side of equation star, and then b is going to be equal to a portion of the right-hand side of equation star, but I didn't include the time variable. So if we rewrite equation star, then we have y equals b times t, and now this is saying that our non-dimensionalized temperature difference is a linear function that depends on the time t. So we're going to use this to then find the convective heat transfer coefficient h. So basically we're going to find the slope b, and then we're going to use this equation here to find the heat transfer coefficient, because we're going to know the slope and we're going to know everything else now. We're going to know the surface area that we have of the rod, we're going to know the mass of the rod, and we're going to know the specific heat for the rod. Okay, so now I just kind of written out what I just said, so we're going to plot y versus t. So y, that's going to be our temperature difference, and we're going to have all of this data from a acquisition device that we have, and then we're going to plot that against time, and our time data, that's going to be recorded as well. So once we plot those, we're going to be able to fit it with a linear function, and essentially we can find that slope b. Once we have the slope, we can use equation 1 that I just kind of added on there, and then we can solve for the convective heat transfer coefficient h. Okay, so we kind of talked about this earlier. We have to verify that we can use this lumped assumption. So this verification is going to be determined it's going to be determined by if our Biot number is less than 0.1. So this has to be less than 0.1 in order to use the lumped assumption. Okay, so the Biot number, that's going to be equal to HL divided by case of S. And we can approximate this characteristic length L by just taking the volume of the rod and dividing it by the surface area of the rod. So if we do that, then we can simplify that to the diameter divided by 4. And if we plug that back in, for the Biot number, we have the Biot number is equal to H times D over 4 times case of S. Okay, so the last part of this experiment is the pitot tube. So if you remember from experiment 2, we used a pitot tube in conjunction with a static pressure port, and then we use that to find the air velocity in the system. So I'm not going to go over this too much since we've done it before, but the air velocity can be found by this equation here, where it's the square root of 2 times the gravity times the specific gravity for the gauge fluid that is being used, multiplied by the ratio of the water density over the density of the air, and then multiplied by delta L times sine theta, where L, that's going to be the length of the gauge fluid height in our column, and then theta, that's going to be the angle for that inclined manometer. So we're using this pitot tube to basically, again, measure the velocity profile in this experiment as well. Okay, so that's it for this experiment. If you have any questions, feel free to email me, or we can set up a meeting in Zoom or something like that. And yeah, that's it. So hope your studies are going well.